So hello students, in this video we will learn calculus of functions of several variables, that is functions which has more than one independent variable. So consider a function f x y where x and y are the independent x and y are the independent variables. So this is a function of two variables. So, for example, if we take say f of xy is equal to say for example x square plus y square. So we have a function f whose domain is r square, that is set of r cross r to r. So this is an example of function of more than one variable or two variables. We can have functions of more than two variables also. For example, if we take the function like this f of xyz is equal to say x plus y plus z. This also gives us a function of more than one variable, that is f is from r cube to r in this case. So these are examples of functions of more than one variables or several variables. We will discuss here in this video further the calculus of functions of several variables, that is, like in single variable, we have learned limit, continuity, differentiability. Like this here also, in case of functions of more than one variables, we'll learn what is limit of a function, continuity, derivatives, on all the things that we have done for calculus of single variable. So let us start one by one. So first say limit of a function in case of say two variables. In case of two variables, I'm writing this that let fxy be a function, let fxy be a function of two variables x and y. If the function fxy tends to a real value tends to a real value L as xy tends to some fixed point say a comma b, then we write this thing as limit xy tending to ab f of xy is equal to L. F of xy is equal to L, or corresponding we can write like this also, that limit simultaneously extending to a y tending to b f of xy is equal to L. So this is just a notation for limits of a function of more than one variable, or say here in this case we have taken a function which contains two independent variables. Also the point to note here is that we have taken functions whose range or whose codomain is a set of real numbers. We are discussing here the functions, we are considering only those functions whose codomain is a set of real numbers. That is, the right hand side will always is a real number. We are not taking any other set in this video. So let us now define what is limit, how to define limit of a function in this case. So you can write like this, that analytical definition of limit. So like this, that let fxy be a function, obviously it contains two variables, then fxy is said to tend to limit L as xy tends to AB, as xy tends to AB, if for any epsilon greater than 0, that is epsilon is any positive number, for any epsilon greater than 0, there exists a delta greater than 0 such that mod of fxy minus L is less than epsilon whenever 0, or whenever 0 less than mod of x minus a less than delta, and mod of 0 less than mod of y minus b less than delta, or correspondingly we can write this condition as like this also we can write like this also, that mod of fxy minus L is less than epsilon whenever 0 less than x minus a whole square plus y minus b whole square less than delta square. So limits in this case can be defined in two ways, either by the first one where we have taken mod of x minus a is less than delta and mod of y minus b is less than delta, or x minus a whole square plus y minus b whole square is less than delta square. So basically we have taken two different regions in this case. So for the first one we have taken this region, that if this is say x equal to a point, say this is x equal to a, and this is say uh, not x equals to a, we can write like this, say let us take the point here, that is if this is say x equal to a, then take a point delta, take a value delta, say this is x minus delta and this is x plus delta, and take your point, say this is b, so this is b, this will be y minus, sorry, b minus delta, and this is say b plus delta. Then this region formed by this one, this and this region formed, that is this portion is actually given, this portion is actually given by this region, this is given by this, that 0 x minus a, mod of x minus a is less than delta, and mod of y minus b is less than delta. So we have taken the region this one, and in the second case we have taken a circle, since x minus a whole square plus y minus b whole square is less than delta square represents a circle in this case. So for example we will have a circle like this, say where this is say our x a minus a comma b point, and this radius is actually delta, so we have defined the limit in terms of two regions. So for example, say while doing problem, if you are asked to find the limit, say find, for example, find limit say xy tending to 2 3, xy tending to 2 3, x square plus y square plus xy. So if we have to find the limit, we can proceed exactly in the same way as we have proceeded in case of function of single variable, but where what we have done in case of single variable, we have just checked whether that the function becomes undefined at the given limiting point or not, and if it is not, then we directly put the value of the variable in that one. So here also we have x comma y, the point x y tends to the point 2 comma 3. So obviously see that if we put x equals to 2 in the function, if we put x equal to 2 and y equal to 3 in this given function, that is x square plus y square plus xy, obviously it is not undefined, so we will get a particular value. So obviously in this case the limit will be, we can directly put the limit, put the values of the variables with the like this, that is equal to 2 square plus 3 square plus 2 into 3 is 2 into 3, which probably gives us is equal to 19. So this is the value of the limit. So we can directly find the limits if the values given are not, I mean, if we put the values in the given function, if it is not giving any undefined value, then we can directly find the limit. For other cases, for analytical cases, means where this type of function we have, where we have to check whether the limit exists or not, that will be discussed in another video. The next concept that we have here is repeated limits. Repeated limits. So what are repeated limits? A repeated limit, a repeated limit, a repeated limit of fxy as y tends to b and then x tends to a is defined as is defined as limit x tends to a, limit y tends to b, f of xy, this one. That means we are taking the function, sorry, that means we are taking the limit first as y tends to b, where we have treated x to be a constant, and then after obtaining the value we take the limit as x tends to a. So this is basically the limit of a single variable, means we are separately taking the limits in case of b, y, and then in case of x. We could have done the reverse also. We could have taken the limit with respect to x first and with respect to y later. That is similarly we could have done like this also, that is limit y tends to b and limit x tends to a, f of xy, f of xy. So one of the important result that we have, we have here is to check if the limits that we have discussed earlier, that is how to check whether limit in this case is not the repeated limit in this case the previous limit that we have discussed, or we can call this to be the double limit. We can call this to be the double limit exists. So one of the most important criteria to check, that means to show that the limit does not exist, is that if limit extending to a and then limit y tending to b, f of xy, and the reverse one, that is limit y tending to b and then limit extending to a, f of xy, if these two are not equal, then we can say that then limit xy tends to ab, f of xy does not exists, but remember in this case, but the converse is not true. So converse is not true means if the repeated limits are equal, we cannot say anything about the double limit. That means if they are equal, then also the double limit may not exist, but we can surely say that if they are not equal, if the repeated limits are not equal, if the repeated limits means if these repeated limits are not equal, then this will not exist. So this is one of the criteria to show that the limit does not exist. Another important criteria is to use this one. This one means what? If we get different, if we get different value of the limit, different value of the limit, choosing by choosing different paths, different by choosing different paths, that is, if the limits, if the limits are not same or unique, we can say not same means if the limits are not unique, then in that case, double limit then the double limit in that case does not exist, does not exist. So I think this will be more clear by an example. So suppose we take an example that limit xy tends to 0 2xy by x square plus y square, 2xy by x square plus y square. So let us choose a path like this. That is, choose a path means say x comma y tends to 0 along this path. Say along this path that y equal to my square. That is the parabola. That means the point xy is moving towards the point 0 through the parabola x equal to my square. X equal to my square. Then what we have? Then what we can write that limit xy tending to 0 to xy by x square plus y square is equal to limit. Now we can put the value of y, means since in this path that we have chosen y x is equal to my square, so in place of x we can put my square into y, my square into y. So I've written this wrong, this was square, this is square, into y square divided by x square is m square, x square is m square y to the power 4 plus y, no, this is also, sorry, it is given wrong, written wrong, this is y to the power 4 plus y to the power 4. Now see, since we have converted this in terms of y, so this is actually that we have to take the limit only in terms of y, that is y tends to 0. So cancelling y to the power 4 from the numerator and denominator, what we have, this is 2m by 1 plus m square, 2m by 1 plus m square. So we got the value of the limit to be 2m by 1 plus m square. Now see this one, that this limits depends on the value of m. That is, if we choose m equal to 1, the value of the limit in this case will come 2 by 2, that is 1. And if we choose m equal to, say for example, say 2, in this case, or say 0, if we choose m equal to 2, in this case the value of the limit will come what? 2 to the 4 divided by 5. So what we are getting, for two different values of m, we are getting two different limits. But we know that limits are unique. We cannot have two different limits. So in this case, the limit does not exist. Because this is one of the procedure to check if the limit exists or not. Okay, we now move to our next part on this one, that is partial derivatives. Partial derivatives. So we have done derivatives for a function of single variable, but we are dealing with functions with more than one variable, say f of xy, that is we have two independent variables. So whenever you are asked to differentiate this function, the question comes that in our mind is that we have to differentiate the function with respect to which variable, since we have two variables here. So in this case we have two different variables. One can be done with respect to x, one can be done with respect to the differentiation, and another can be done with respect to y. So the derivative that can be done with respect to x, we denote it by del f del x instead of the previous df dx. So we have now del f del x. And similarly, the derivative that we will do with respect to y will denote it by del f del y, del f del y. So while differentiating, so differentiation procedure is that while finding finding del f del x, the variables the variables other than x should be treated as constant. Similarly, in case of del f del y, whenever we will differentiate the function or we will find the partial derivative with respect to y, we have to treat the other variables as constant, and then rest the procedure is exactly same as we have done in case of single variable, For example, say if we consider the function say like this, that z is equal to not z, say if you consider the function say u is equal to uh, x by y plus y by z plus z by x, and if you're asked to find the derivative of u with respect to x, because we have three variables here x, y and z. So whenever we'll differentiate the function or we find the partial derivative of u with respect to x, we will treat the other variables, that is we'll now treat the other variables y and z to be constants. So differentiation of x by y in this case will be 1 by y, because differentiation of x is 1 and 1 by y is constant in this case. For the second term, no x is involved, so differentiation of that function gives you 0, because differentiation of constant is 0. And the last one is z is a constant and differentiation of 1 by x gives us minus 1 by x square. So what this gives? This gives us 1 by y minus z by x square. So this is the partial derivative of u with respect to x. Similarly, if you want to find the partial derivative of x with respect to y, so we have to do similarly, we have to treat now as x and z to be constants. Now, so if you have x and z to be constant, so if you now x is constant, the derivative of 1 by y will give us minus 1 by y square. In the second term, 1 by z will be there and derivative of y will give you 1, and the third term involves no y, so the third term will give you us 0. So what we have, this is 1 by z minus x by y square. So similarly, we can find the other derivatives, not only with respect to x, y, z, we could have find derivatives of second order also. So we have to differentiate accordingly with respect to x, y, z similarly. So easy thing. Now, analytically, what we have done in case of single variable, we know that we have defined f dash x by this limit, that limit x tends to limit h tends to 0 f of x plus h minus fx by h. So similarly here also, by the similar procedure, we can define del f del x to be as limit h tends to 0 f of x plus h, comma the other variables involved, say for example y, minus f of x comma y divided by h. Similarly, if you are differentiating with respect to y, so we have to treat x as constant. So in this case, we'll write this as limit, say for example, taking another variable k. This will be f of x comma y plus k, since x is constant, minus f of xy divided by k. So these are the definitions or analogous definitions of the derivatives in terms of limits, exactly in the same procedure. Similarly, we could have defined the partial derivatives, the second order partial derivatives. For example, say del 2f, del 2f, del x, del y. So this is nothing but this is del x of del x of del f del y, del x of del x del f del y. Now we know how to find the value of del f del y. So we'll find the value of del f del y and then we'll operate again del x on that operated value. So what we'll get in this case is limit, this is what, say limit h tends to 0 fy of, I'm writing this one, fy of, so before this, okay, sorry, before this let me see, write this one, that del f del x is also denoted like this, del f del y is also denoted like this. So let me write this again. So this is nothing but, del x of del f del y is fy. So now we use the concept of derivative with this one on this function. So this is limit h tends to 0. Now our given function is fy, and fy is fy of x plus h comma y minus fy of xy divided by h, where we have to find this value and this value separately. That means fy at the point x plus h comma y, fy at the point x plus h comma y, which is nothing but del y of this function. So this is limit k tends to 0, f of the function is now x plus h will be constant, since we are differentiating with respect to y, the variable with respect to x is constant, and this will be y plus k minus f of x plus h comma y divided by k, and if y of xy is nothing but del f del y. So we have to separately find this value, then this value we have to put the values here, and then we have to calculate the limit to find this mixed derivative. So these are the definitions of the derivatives in terms of limits. Okay, so next what we have is the chain rule. The chain rule that we have done in case of single variables also. So I'm writing like this, that say suppose f is a function and it has two variables x and y. Suppose say x again is a function of another variable t, and y is also a function of another variable t, the same variable. That is, f is a function of xy, and where x is say another function of t, say phi t, and y is also a function of t, say psi t. So actually what we have, that f is a function of a single variable now t. F is a function of a single variable now t. So we can find df dt then, since this is a function of single variable. So now df dt in this case will be defined like this. This is del f del x into dx dt, since x is a function of t, plus del f del y into dy dt. So this is the chain rule. When f is a function of x, y, and x and y is a function of another variable t, x and y is a function of another variable t. You can have like this case also. This is case number 1. Say number 2, we can have like this, that F is a function of, say, u and v, where u and v are another functions of x and y. Where u and v are another functions of x and y. Now what we have is that f is actually a function of two variables x and y. So in this case, partial derivative will come. This is del f del x. So if you want to find del f del x, so by chain rule it will be having like this. This will be del f del u into del u del x. We are taking del because u also contains two variables x and y. So we are using partial derivatives, plus del f del v into del v del x. Similarly, if you want to find del f del y, this will be nothing but del f del u into del u del y plus del f del v into del v del y. We could have used this method for more than the two variables also, so we have to just proceed similarly for the variables that involves here. Okay, so let us take an example for this. Say for this that we have a z equal to function of xy, a function of xy, where x is equal to e to the power u into cos of v, and y is equal to e to the power u into sine of v. So first relate what it is given. So it is given that z is a function of two variables x and y, and x and y are given functions of two variables u and v. U and v. We are asked to find del z del u del z del v, del z del v. Now del z del u by chain rule, how it will be? It will be like this. Say, so del z del u will be means x, z, x and u, and then z, y and u. So like this. So what we have here? So we'll have here del z del x into del x del u plus del z del y into del y del u. Now from this is given x is equal to e to the power u cos v and y is equal to e to the power u sin v. So we can find del x del u. So del x del u will be e to the power u cos v, and del y del u is also e to the power u sin v. We can find the other derivatives del x del v. So in that case the derivative of cos v will be minus sin v, so it will be minus e to the power u sin v, and del y del v in this case is e to the power u cos of v. So just put the values. Del x del u is e to the power u cos v del z del x plus del y del u is e to the power u sin v del z del y. Similarly, del z del v. So del z del v will be del z del x into del x del v plus del z del y into del y del v. Just put the values. So del x del v we got minus e to the power u sin v into del z del x plus this is e to the power u cos v into del z del y, del z del y. So these are the application of chain rule. Okay, the next one that we have here is homogeneous function. homogeneous function. Say a function fxy is said to be homogeneous of degree n if f of tx ty, that is replacing x and y by tx and ty, gives us t to the power n into f of xy, t to the power n into f of xy. Or correspondingly we can write like this also, that if f of xy is equal to x to the power n into some function of y by x into some function of y by x. For example, say fxy is equal to, say for example, x square plus y square. So find f of tx comma ty. So this will be tx square plus ty square. This gives us t square x square plus t square y square. This is equal to t square into x square plus y square. This is nothing but t square into x square plus y square is f of xy. So what we got, that f of tx comma ty, f of tx comma ty is t square into f of xy. So we can say that fxy is homogeneous. Fxy is homogeneous of degree 2. Fxy is homogeneous of degree 2. Now, for homogeneous function, we have a very important result and an interesting result. We call this to be the Euler's theorem or Euler's theorem, and it states that Euler's theorem. It states that if f of xy be a homogeneous function, f of xy be a homogeneous function of degree n, then x into del f del x plus y into del f del y is equal to n into fxy, is equal to n into fxy, and for more than one, means for more than higher one derivative, or say for higher derivative, it will be like this, that uh, x square into del to f del x square plus 2xy into del to f del x del y plus y square del to f del y square is equal to n into n minus 1 into fxy. That is, we can write this as similarly as, say, uh, x into del del x plus y del y whole square of f is equal to n into n minus 1 fxy. We can proceed this one with higher degrees, means higher orders. For third order, fourth order, we can proceed similarly. We are not going to discuss the proof of this. We are doing the application of this, means how to use this in problems. So let us use this in a problem. So how to show this? What to show this one? Say your function, say u is equal to tan inverse of x cube plus y cube by x minus y, and you are asked to check, or you are asked to prove that del x into del u del x plus y into del u del y is equal to sine 2u is equal to sine of 2u. Now see, from the given function we can write that tan of u is equal to x cube plus y cube by x minus y. We denote it by, say, for example, f of x y, f of x y. So now find f of tx comma ty. So this is equal to t cube x cube plus t cube y cube by tx minus ty, that is equal to t square into x cube plus y cube by x minus y, that is equal to t square f of x y. So what we have, therefore we can say that if xy is homogeneous of degree homogeneous of degree 2. So therefore by Euler's theorem, so what we have, therefore by Euler's theorem we can say that x del f del x plus y del f del y is equal to n into f. So this is x into del del x of f is, say, f is actually tan of u plus y into del del y of tan of u. This is equal to n is now 2 and this is tan of f is tan of u. Now just calculate it, simplify the function. So this is derivative of tan u with respect to x. So derivative of tan u gives us differentiation of tan x is sec square x. So this is sec square u into x del u del x plus sec square u into y del u del y is equal to 2 tan x. So simplify and take the values. Of means, sorry, multiply sec square u in the right hand side, divide sec square u in the right hand side. So this will give us x del u del x plus y del u del y is equal to 2 tan x, 2 tan u by sec squared u, which is nothing but sine of 2. So these are the applications of homogeneous function and Euler's theorem. Homogeneous function and Euler's theorem. Thank you.